Okay, who remembers what we learned last week, if anything? Too many assignments. Are you guys super busy nowadays? You guys are going to have 2 weeks break, though, yeah? In Canada, this is called a reading week. I think in Australia, it has sort of a better name. Because for our reading weeks, we'd all just fly down to Cuba or something and have a week off school. Did those web assigns go okay? Did you guys do the long one with the vector fields where there was like 100 questions and it was okay? Okay. I was worried you guys would get really mad at me for assigning you so much work. So last week, I think we discussed, was it vector fields we did last week? Okay. So, jeez, Murphy. So we're going to continue. So that was really the beginning of what we call vector calculus. So now we're going to learn about some different types of integrals, which are sort of, would be obvious. You're going to sort of think, why didn't we do this before we did the volume integrals? But the order of this is sort of irrelevant. So we've seen how to integrate over various regions, right? So if you're in R2 and you have a curve, we can ask for the area under the curve. If you're in 3 space and you give me a surface, we can ask for the area under a surface. But what happens if I give you a space curve in 3D and ask for the area that's bounded by that space curve? Right? So imagine that you draw some sort of, I have a picture. You draw some sort of curve in space, and you want to calculate that area. So this is sometimes called a curtain, right? Because it's like you're hanging a curtain from the top curve so that it hits the bottom. So the first half of this lecture, we're going to spend developing techniques for determining the area on the projector here. So first we need 2 things. We need some surface F and some curve C. Right? So F here is actually a surface, but I've restricted the surface to the part that's over the curve that we are integrating over. Right? So you have to imagine that you have a surface and that we take this surface and we only look at the part of the surface that's above some prescribed curve in R2. So I hope you remember all that stuff we did with curves at the beginning of the year. Right? It was not for naught. It was for this. Okay, so how can we calculate the area under the curve here? Well, our typical strategy was to calculate the area of a segment and then add up those segments to get the total area. So one of these such segments is highlighted in blue here. So along the bottom, right, so what do we need? We need something to sample. Well, obvious candidate for sampling when you have curves that are parameterized by t is to divide t into pieces, or a little bit more complicated would be to divide this curve itself. So last week, we determined how to calculate the length of a curve. This means that we can break any curve into equally spaced pieces. Right? If we can calculate the length of it, we can divide the length by n and say, okay, well, let these individual pieces here be equal parts of C. That would be pretty hard to set up if we wanted to, but we really don't ever go in and calculate them explicitly. All right, so our sample points here are going to be t's, and we're going to choose t's so that we are equally spaced along that curve C down there. So now that we've segmented our t's into intervals, we can count them, t1, t2, t3. Here's the ith one. So this curve C at t, I, gives you 2 coordinates, an xi and a yi. And if we take f and evaluate it at xi, yi, that's going to give us the height here. We're now interested in calculating the actual area of this blue thing. And we're going to have to do some calculus trickery in order to do it, right? Because this is sort of an irregular shape. Right? You have a curve on the bottom, you have a curve on the top, and you have multiple different sort of heights to take. So this is what we're going to do instead. We're going to say if we want to calculate the area here, AI, of this segment between RTI and RTI plus 1, right? So we we have an interval in t. We choose a sample from that interval, as we always do, and we say, okay, let that be the height, so that the distance from here to here is approximately equal to what? So what's the problem here? We're on a curve, right? And we want to say, well, I need the length of the base, but the base is a curve. What have we been learning this whole time about when we make distances very small? That was the correct answer, whoever mumbled it. Straight line, right? If RTI and RTI plus 1 are close enough together, then the curvature doesn't matter. It's basically a straight line. So this, oh, I thought I had another. Okay, well, that will be this picture. So let me come back to that. I think first I want to actually give you a definition for a line integral. So if we say delta SI is the distance between 2 points on this curve, then this area is approximately the length of this curve times this height. Right? One of the heights will do. It's not going to be exactly equal to it, but it will be so approximately, and if these two things are close enough together, then we're okay. So the definition of a line integral, you give me a surface F, you give me some smooth curve C, that's in R2, and we want to go through F, right, restrict it to C, and then sum up these areas, right, that the curtain is giving. Right? So we have this curtain, we're cutting it up into little trapezoids and then adding the areas. Right, so this is the typical limit definition of the integral, but we want to be able to practically compute this, right? So let's do a little bit of work to see how we can actually go and compute this length. As I just said a minute ago, the relevant thing to notice here is that if these 2 points, ti and ti plus 1 on that curve C, are close enough, then we don't really need to account for the curve, right? We can just take a straight line from here to here. So this distance, given by this black line, is approximately equal to the distance from here to here on C, where that approximation becomes better and better as these things get closer to each other. Are you familiar with this notation? A lot of things use double lines like this. This means the distance, right? This is the length of this vector. So the length of the difference of two vectors gives you the distance between those two vectors, right? So this is just notation for this distance. And it's the square root of the sum of squares of the individual components. This is actually called the magnitude or the 2 norm. Right, so now we can swap out that delta SI with this distance instead. Right, so before this we had AI is equal to this height times delta SI, but now we're replacing delta SI with something more explicit. Right, that is the linear distance between these two things. So if we break AB, the interval from which t is taken, into n intervals, and we let ti be the ith one, our ith sample, then the area under FRT, right, our surface restricted to a curve in R2, is approximately given by this. And let's unpack this a bit. Right, so we start off here. We want to take the sum of n of those pieces of curtain. This is the height, and this is the base, right, to get the area. Taking this, we can expand it, right? So R evaluated at Ti gives you an XTi and a YTi, and R evaluated at Ti plus 1 gives you an XTi plus 1, YTi plus 1, and therefore the distance between those things is the square root of the sum of the difference of squares. If I rewrite this in a more familiar way, right, you see here this is x at Ti minus x at Ti plus 1. We normally write the difference of consecutive x's as delta x, and the difference of consecutive y's as delta y. And then I can multiply by delta t. I can remove a delta t from this square root. I multiplied by delta t here, but divided by delta t. I multiplied by 1. And this is very popular in math. This is where you get all these magic steps. But you see that I've taken this sum and turned it into this sum. Right? So we're getting closer and closer to actually being able to practically evaluate a line integral. So notice if this distance, the change of t, gets smaller, tends to 0, we're going to get successively better approximations of the lengths of R, right? Because the discrepancy was the fact that we're taking bases as lines when the bases should be curves. But that will eventually disappear in the limit. So to get delta t goes to 0, we need to take the number of intervals that t is divided into to infinity. And borrowing arguments from the last lecture where we determined the length of a curve, we can make this type of argument. So the limit as n goes to infinity, as the sum from I equals 1 to, okay, I'm just going to say this in English. If you take your interval t divided into n many pieces, and you sum the heights at those individual t's and multiply by this distance, this line, that is exactly equal to the, well, by definitionally, right? To say that these things are equal is sort of misleading because this symbol here is just a symbol, again, for taking limits of infinite sums. Right? So this is equal to this by definition. So we can find the line integral by taking the integral from a to b of f evaluated at rt, square root of dx, dt squared minus dy dt squared dt. Right? When all of these changes get infinitely small, we swap out the delta with this differential d. And what does this mean? Well, rewriting this, that the line integral from a to b is given by f rt dot, this is a scalar dot product, the length of the derivative of r. Do you see how this and this are the same? Right, this says take the derivative of all the components of r and then take the sum of the square. Oh, why is this a difference? Shouldn't this be a sum? I think that may be a plus. But in any case, this is the limit we're interested in doing, these line integrals. So if f is defined over a smooth curve r, parameterized by t, then the line integral of f along, so let me just, oh no, this is the proposition I need. Then the line integral of f along r, right, the integral along this curve c of this surface ds, is equal to the integral from a to b of f evaluated at rt times the square root of dx dt squared minus dy dt squared. I'm going to have to check if this is not a plus. But really, this is all you need here. Right? If you didn't understand anything up until this point, just knowing that we've defined the integral, the line integral over this curve c of this surface ds is equal to this quantity here will be gravy. Right? So the value of the line integral does not depend on the parameterization of the curve, right? Because there's an infinite amount of them, provided the curve is traversed exactly once, right? So we have a curve, and we're adding areas on top, so you can't keep going around in a circle. You can't just keep adding areas and areas together. So here's a real question. Let C be the upper half of the unit circle, and evaluate the integral over that unit circle of this surface. So before we were doing questions very similar to this, except this was an inequality. We would have something like less or equal. Before we were dealing with regions, now we're really just dealing with lines. So how can I evaluate this? Well, first we need a parameterization of the unit circle. What is a parameterization of a unit circle? That would be the case if we were in polar. But yeah, we can parameterize the circle by t, taking t from 0 to pi, right, because we want the top half. And that curve is, cos t sine t, right? So if our curve is cos t sine t, then the derivative of its vector equation is minus sine t cos t. And using the proposition, the integral over the top half of the circle of this surface ds is equal to taking this equation and evaluating it at RT, which I maybe didn't explain too well. But this says what? This says x gets cos t and y gets sine t. Right? So we're going to get 2 plus cos squared t sine t. 2 plus cos squared t sine t. Dot product the magnitude of the derivative of that r, right? Minus sine t cos t. So this is going to evaluate you the square root of the sum of squares, sine squared t plus cos squared t dt. What does this work out to? Well, sine squared t plus cos squared t is 1, so that disappears, right? So all we have left is 2 plus cos squared t sine t dt. If we take the integral of this, we're going to get 2t minus cos cubed t over 3. Okay. This sine t is going to fall out because of the chain rule. We need to evaluate this from 0 to pi. We love zeros, so let's do the top one first. That's going to be 2 pi minus cos pi cubed. What's cos of pi? Cos of pi 0? No, cos of pi is minus 1. And minus 1 cubed is minus 1. So this should be 2 pi plus a third? 2 thirds. Am I missing a 2? Oh, cos of 0 is 1. Yeah, so you get plus a third, 2 thirds. Okay, well, those little details are less important than the setup. Okay, so here's another curve. You don't necessarily have to have one curve defined by one equation. You can have one curve defined as a bunch of different curves, provided they have endpoints that begin and end appropriately, right? So this can be from A to B. This can be from B to C, C to D, D to E, E to F. Right? But the important part is that they're connected at these points, and the orientation, the way that you're moving through this curve is consistent, right? You can't go from here to here and then have this be the other direction. And so this is our notion of a piecewise smooth curve. Now we have this proposition, if you have some sort of curve C, which is the union of a bunch of other curves, where again, the terminal point of one of the curves is the initial point of the next, then as we expect, the integral over this curve is equal to the integrals of the individual curves summed. Here's an example of that. Suppose I give you two curves given by C1 and C2, where C1 is simply the sort of first part of the parabola, and then we just have a vertical line. Let's try and evaluate this integral. So the first thing we're going to need to do is what? What always has to be true about our C1 and C2? How do they have to be represented? Well, no, this is only what's in the R2. You have to imagine that there's a surface on top of this, which I haven't drawn, right? So we're interested about what is happening to the surface above this if we're drawing some curtain. But let me just go back to the proposition of line integral. What's C in this proposition? Our C has to be given by a parameter. We need to have some sort of R, some parameterized curve, in order to utilize this expression. Right, so the first thing we did in this question was parameterize the upper half of the circle. That was our C. So what's the first thing we have to do for this question? Parameterize C1 and C2. Right? What's a parameterization of C1 look like? Well, it's the parabola, right? What are the points of a parabola? That one's easy. T squared. Right? Those are the points of the parabola. Functions are easy, because functions are always written y equals some function of x. And so that means the parameterization of any function is always t f of t. So the other one is what? Well, x doesn't change. X equals 1. and y goes from 1 to 2. Right? That's that parameterization. So we have the parabola as t goes from 0 to 1. We have this vertical line, which is not a function, as t goes from 1 to 2. And just as it's good to check that the terminal point of this is the initial point of this, just to see that we've set up everything, right? So if we put 1 into here, we get 1, 1. And we put 1 into here, we get 1, 1. Right? So we at least know that we have a continuous curve with no jumps. Okay, now we know that I can take this integral and break it up into two pieces, right, where I can deal with the C1 and C2 individually. So let us do so. Okay, here's the C1 integral. So recall that our parameterization of C1 was tt squared. So what happens when I evaluate this function f at R? What is this saying? This is saying, well, x gets t, and y gets t squared. So what does this become? Well, it becomes two, I think I did 2 steps here. It becomes 2 xt, or just t, times the magnitude of the derivative of this, which is 1, 2t, which is 2t, and then the square root of the sum of squares, which is 1 squared plus 4t squared, and then we just integrate from here to get 5 root 5 minus 1 over 6. All right, but what were the steps? We had a curve C1, we had to parameterize it, then we had to run this function through that parameterization, and then also find the derivative of this. So let's try it again. So here's the second integral. Here is our second curve, C2, which says replace all x's with 1s and replace all y's with t's. So this is going to become 2. The derivative of R2 is what with respect to t? What's the first position? Second? Cool. All right, so I should have put a 1. But 2 times 1 is 2. What's the magnitude of the vector 0, 1? It's the square root of the sum of squares. Square root of 0 plus 1 is 1. Right, so this boils down to the integral of 1 to 2, 2 dt, 2. Yes? Well, the signed area is always positive when we're moving in this direction. You can't have negative distance. Right? The magnitude is defined to be the distance between 2 points. That can't be negative. So by convention, then, I guess we're always taking the positive part of the square root. Before I forget, I made course notes for you guys. Took me a long time, but they're there now. There's now a course notes version of the slides. Yeah, they're done. Up till, well, I didn't do this lecture yet, but they're done. No problem. So I hope you guys go and download that. Otherwise, all of that work would have been for naught. I'm not here now. I'm gone at the end of this semester. Going to Queensland. Yeah. Come to love the cockroaches. Okay, so if we add the remaining 2 answers, we get this. Right, so again, remember, C, parameterize C, and then just use that proposition. And if the only thing you want to take is the practical manner to which you actually have to calculate line integrals honestly are pretty easy, right? Provided that you can actually parameterize your curves. Because you guys should be getting pretty good at integrating by now. Is that the case? You guys can do single variant integrals? I want to get you to a point where you can't believe you didn't understand calculus last year. Like that, I would be satisfied if you're like, oh, that was so easy. How come I couldn't do that? I'd only ever understand courses I was taking until the semester following. Okay, so we have this notion of, so we calculated a line integral with a parameterized curve. But sometimes for technical reasons or for practical reasons when you're doing math, you want to keep your equations as equations of x and y. Right? Suppose you don't know how to parameterize your curve, for instance. Well, we can do that too. And those are the definitions. I'm not going to geometrically sort of demonstrate to you why this should be the case, but here's the proposition which is required to do these special types of integrals. Yes, this should be a y. No, always assume that I've been making mistakes. These are all fresh slides, so this is all from my creation. If you find mistakes in the course notes, please email me. I'll try to keep a list of what I've received. And if I'm allowed, I may give out some marks for mistakes, if Bjorn will permit me. Okay, where was I? Okay, so we take these line integrals, and you can do it by sort of counting all the contributions in the x direction and counting all the contributions in the y direction. And it's the same type of calculation, just done differently. Right? And as it frequently happens that these types of integrals occur together, if you see something like this, all right, the integral over this curve C, pxy dx plus qxy dy, this is technically not, we're sort of messing with the notation here. This means this. And so we just factor out that integral sign if you wanted to give it that way. But again, mostly we're concerned about how we actually go and do this on tests and assignments. So here is a question. Find the line integral of y squared dx plus x dy over this region C1, which is the line segment from -5, -3 to 0, 2. Okay, so what is the parameterization of our line segment? Because we still need that. Bless you, bless you. How do you parameterize a line? Well, I already told you one way of doing it. I said it's easy to parameterize any curve which is a function. If you have y equals fx, the parameterization is always going to be t f of t. Well, can you give me the function for this line? Tell me you can find the equation that goes through 2 points. I give you 2 points and I just want the line between them. How do you do this? Yeah. This whole, you need y equals mx plus b, right? So I'll just do it for you. But this should be, I'll show you an easier way of constructing line segments in 3D. You could do it like this, if you want to think of it this way. If you have 2 points in space, and I'm going to do this again later with the slides, but if you have 2 points in space, you can start at one point and walk in the direction of the other, right? And then you use a parameter t, which goes between 0 and 1, which really represents the percentage along that direction you've got. So you can go halfway between P to Q, all the way from P to Q. So that's what this parameterization is saying. It's basically saying, well, to get from -5, -3 to 0, 2, start at this point and walk in the direction of the gradient to 0, 2. I will develop this a little bit later, but here you go. Here's the equation. Here's the parameterization of that line, which you can find by doing y equals mx plus b. Okay, so the line segment is parameterized by this. Could that be right? What's the slope between this guy? Rise is 5, run is 5, 1. Okay, so supposing the line segment is parameterized by this. This is our x component here, and this is our y component here. So this is the relevant deduction. Because we need to replace this dx and this dy with something. So if we know that x is equal to 5t minus 5, which is from that component, this means that dx, the derivative of dx by dt, is 5, right? Which means that we can rearrange this equation here to say dx is 5 dt. We can do the same thing with y, which says 5t minus 3, which means that the derivative of y with respect to t is 5, which means that the dy is equal to 5 dt. Right? So just remember these values here. Because now I'm going to take this, and I'm going to replace this dx and dy with our 5 dt and our 5 dt. Just happen to be both the same thing. We need to move from 0 to 1. And now we need to evaluate y squared and x at a parameterization. And remember, y is getting 5t minus 3, and x is getting 5t minus 5. 5t minus 3 squared is 25t squared, I don't know, and so on. Oh, no, I just wrote it like this. 5t squared minus 5 squared, 5 dt, plus 5t minus 5 times 5 dt. Which one? There's definitely some mistake in here, yeah? Yeah, one of these guys should be a 3. It should be, this should be a 3. Or could be the previous page. I don't know, I'll have to double check. But again, it's more the setup which matters than my poor arithmetic. We're gonna set it up so that these questions, like the majority of marks, are given for the setup. Last year is when we cared about like you being able to integrate. The assumption now is that you can integrate, but yeah, I'd say the vast majority of the marks for these questions will simply be setting up the integral. If you do that wrong, then everything else will be wrong. Right? So spend most of your time learning how to set up these integrals properly. Because I can assure you that on your final, we're not going to give you some crazy, like there's not going to be crazy integrals that you're going to have to do as intermediate steps here. We want you guys to do well. It reflects poorly on us when you do poorly. Okay, so we have an integral now in a single differential dt here. So we can combine all of this, and I hope from here it's easy to integrate. This is simply a polynomial in t from 1 to 0. So we do this, and we evaluate from 1 to 0 and get minus 5/6. Here's another one. Evaluate y squared dx plus x dy. Same question, different region now. Right, so C2, this is a little bit more complicated. It's the arc of the parabola, and this is a parabola rotated. It's a parabola in this direction. And we want to use the path from minus 5 minus 3 to 0, 2. Oh, so this time I didn't draw it. So we can parameterize C2 by what? Well, if C2 is a parabola, if y gets t here, then x gets 4 minus t squared. Right? Parameterizing curves is very easy if something is isolated like this. Right? Just if y gets t, then x gets 4 minus t squared. And where do we have to move from? Well, it's a little bit more complicated. So we need to start at minus 5 minus 3. Where does that happen? For what value of t? Well, we've parameterized y, right? And y goes from minus 3 to 2. So that's where this comes from. Right? This is the portion of this curve between these 2 points. Yeah, this is why I didn't want to do general curves on the first lecture, because I knew we'd all forget it by the time it was relevant. But if you just look at the points that this generates, right? If you put t equals minus 3 into here, you get this point, right? 4 minus 9 is minus 5. Minus 3 gives you that. If you put a 2 into here, you get 0, 2, right? So at least the endpoints work out. And I'm saying you're going to get all the other points in between. And go back to those lectures if you need a refresher. Okay, so now that we have an x component here and a y component, we just take the derivative of the first, which is going to give us dx by dt is minus 2t, And isolating for dx says dx is equal to minus 2 dt. This says y equals t, which means dy dt is 1, which means dy gets dt, right? So here are our substitutions. We're going to replace dx by minus 2 dt, dy by dt, and we're going to go from minus 3 to 2 in t. From here to here, just multiply by dt. Am I missing a t? Yes. So this should be dx equals minus 2t dt. Check and make those corrections on the fly. Did I do it right here? Well, first of all, one of these should be a y. How did I screw this up? I think all those y's should probably be t's. All right, so let's do this on the visualizer since I sufficiently messed this up. Although I may have to use this one. I don't know what echo. I checked the echoes and it's not showing the visualizer. Documents. Okay, so let's try this one from the get-go. So what I want to do, I want to evaluate over C y squared dx plus x dy. And I want to go from, so I have a parabola. How does this parabola look like? X is 4 minus y squared, so minus y squared plus 4. It looks like this, I believe. I hope that's right. Minus 5, minus 3. Zero. Okay, so I'm saying that this is parameterized by 4 minus t squared t, such that t is from minus 3 to 2. All right. So this tells us what? Well, this says x is equal to 4 minus t squared, means dx by dt minus 2t, which means that dx is minus 2t dt. Similarly, we have y is equal to t, that dy is equal, dy dt is equal to 1, which means dy is equal to dt. Okay, so now let's look back at our original integral here. This is going to become what? Well, I need to evaluate y squared at what our new y is, which is t. So we get t squared. Our dx becomes this, minus 2t dt, plus x, which is 4 minus t squared, times dy, which is dt. Okay? And what's our bounds? Well, our t goes from minus 3 to 2. Yeah, I think on the slides I just put y instead of t. But anyways, from here we just simplify. What do we have? We have, there's a t squared. This is going to be a t cubed. Integral from minus 3 to 2 of 4 minus t squared minus 2t cubed dt. Yeah, so I just, everything, all the y's here should be t's, but that was still useful maybe. All right. So we just did two integrals over the same surface, but we did two different curves. Right? And notice that even though these curves begin and end at the same endpoints and terminal points, well, they have the same terminal and initial points, the integral is totally different. And this shouldn't be a surprise, right? If you imagine some surface and I draw some shape in R2, you wouldn't expect that curtain to have the same area as any other curtain that you could draw. And for instance, you could go way further out here and make some loops if you want, right? But the areas are going to be different. So in general, the value of a line integral depends not just on the endpoints, but also on the path itself. Right? And oh boy, that is not. Okay, maybe I'll do that for the. Hold on, maybe I can. Okay, so here's two curves. They're the same curve, but the second curve has the reverse orientation of the first. Right? So this is what we denote as minus c. So the relationship between, oh geez, I just wrote the most obvious statement here. Did you know that the integral of c f of x dx ds is equal to itself? Okay, what am I trying to express here? Does anyone have any guess? Pretty much. Right, I want to say that if I integrate over this curve C, that you're going to get the opposite. You're going to get the negative signed area that if you were to traverse the curve in the opposite direction. Right, so there should be a minus here and a minus C down there. Okay, so I'll fix that. But do the previous question, but reverse the direction of the curve. Yeah, you can think of it. You can think of it that way, right? Except when you switch the bounds on a planar integral, you had to change the sign because you're moving in the reverse direction, and had to account for that in terms of because your steps then become backwards. You're taking negative steps. But just remember that if you integrate over the same curve, but traverse the curve in the opposite direction, that you're going to get 0. This is useful when you're doing physics and stuff because things will cancel. You'll have very sophisticated expressions, but you can say, "Oh, look, this is the same surface, and we're doing a line integral in one direction and then the reverse, so we can just cancel them." So go ahead and confirm this. It's good practice for a variety of reasons. Line integrals in space. No one's seen that Muppets movie? Very disappointed. Okay, so we've done line integrals, so with a restriction that one of our integrals was in the plane, right? That you had R2 and you drew a curve in it, and you found the area that was bounded by some surface to that curve. Nothing really is preventing us from drawing a curve in 3D and doing the same thing, right? So instead of the curtain falling all the way to the ground, the curtain falls all the way to where the line stops. And the only thing that you need to know here is that we have a very similar equation. In fact, it's the exact same equation. And so the same techniques that we're working for the 2D case is going to work exactly the same thing for our 3D case. So maybe I fibbed. This F here is a 4D surface. Right? So we're sort of jumping dimensions. So I didn't draw a picture because that would be very impossible. Well, I could do an animation, but I don't have that much time. Okay, so this is what you need to know, that if we want to take the integral of this surface over this curve C, that if we can parameterize the curve C by some function r, then this integral is equal to this integral. Right, and we are able to integrate this. Here's a lemma. The curve C is parameterized by this r, then the line integral of the surface 1, the constant plane, over C gives you the length of C. This is the case for all of the types of integrals that we were doing. And we could triple integrate over 1 to get a unit volume and an area if we were doing that in planar. But that's just an interesting consequence. But this is the real meat. This is the type of questions you'll be seeing on your midterm, well, actually, on your exam and in your web assign. Evaluate the integral of y sine z ds over the curve C if C is the circular helix given by the equations cos t, sine t, t. And so this one's a little bit easier because the parameterization is given to you. Oh, there should be a comma in here. All right, so let's continue. Let's use the equation that we were given on the last proposition, this one down here. So 2 steps, right? We're going to have to evaluate f at RT and then find the length of this tangent vector. Okay, so what is the derivative of r with respect to t? And 1. Cool. And then what is this equation turn into once we run it through this? X gets cos t, y gets sine t, z gets t. Sine squared you run it through the original. So t, yeah, we're going to get sine t times sine t, which is sine squared t, as you said. So here we go. I get this is equal to 0 to 2 pi. That's the interval t was given on. Sine t, that gets subbed in for y. This sine t comes from here because z gets t. Then we have to multiply by the length of the tangent vector to this, which is minus sine t cos t1. And the length is given the same way. You take the sum of squares and you take the square root of that. So you get sine squared t root sine squared cos squared plus 1. How does this simplify here? Sine squared t plus cos squared t is 1. 1 plus 1 is 2. The square root of that is root 2. Right, so you could take that root 2 out. I change sine squared t into its equivalent form using double angle formula. Since people were yelling at me about table lookups, I'll skip it, right? That's how you usually get rid of powers of on trig identities, is by using the double angle formulas. And then we just continue where now this, did anything change? No, that was useless. But you just continue routinely and you can work this out to root 2 pi. Now, those are very interesting numbers, root 2 and pi. Okay. Okay, so this is what I was alluding to before. You will frequently have to parameterize a line segment, right? That is, you only want the points that are in between 2 points and nothing beyond, right? Lines are infinite. Line segments are finite, right? So as I said, you can think of it like this. You have a point P, you have a point Q. You know that sort of you have a unit direction, and then you just move some percentage down, right, that unit direction, where 100% gets you from P to Q. So I'll show you how to work this out. So you can parameterize the line segment connecting P and Q in R3 by this equation. RT is equal to 1 minus TP plus TQ, and T runs from 0 to 1. Right, so proof. Start at P and travel in the direction Q minus P towards Q. Right? Q minus P is that direction. Regarding T in 0 to 1 as the percentage traveled along Q minus P, then the parameterization can be written like this. So is this understandable, or should I draw a picture on the visualizer? Visualizer? Because this is a neat way of remembering this. Center right. Maybe I'll use this red pen instead. Right, so what's our task, right? We have P here, and we have Q here, right? And we want to parameterize this line, right? And only this line. So I'm saying, well, if we start at P, we want to get to Q, right? Well, I know that this direction here is the vector given by PQ, which is what? What's the vector PQ? Q minus P. Right, that's how we do that. So if I start at P, and I move in the direction Q minus P, and how far do I move along it? Well, T. So I put the brackets on the wrong thing. So you can imagine this is like T percent. Right? So if T is 50%, you'd be here, 75%, you'd be here, and 100% you'd be here. So we don't use percentages, we use their decimal form, right? So all the T's between 0 and 1 are the same as all the percentages between 0 and 100. Right? So this line segment is parameterized by this. Right? And if I just simplify this a bit, you get 1 minus TP plus TQ. Okay? But you can always remember that you can always work out this equation again by just thinking I need to go some percentage down the direction to the other point. You can always rework it out. Okay, so here's another question. It's this line integral where we're doing it with respect to each direction because we want to keep everything in x's and y's. And we're going to do it over two line segments where the terminal point of this line segment is the initial point of this one, so we're okay. What now is the parameterization of these two curves? Well, I gave you the equation. Right? It's 1 minus t times the first point plus t times the second, which gives us 2 plus t, 4t, 5t for our C1. Right? So we're going to do this in two pieces, the C1 piece and the C2 piece. If this is the parameterization of the line, that means x is 2 plus t, which means which means dx by dt is 1, which means dx is equal to dt. dy by dt is 4, right? That's the derivative of 4t with respect to t, which means dy is equal to 4 dt. And the derivative of z, which is 5t with respect to t, gives you 5, which says dz is equal to 5 dt, right? So we're going to take these values and put them in for these ones here. We're going to have to replace y, z, and x with 4t for y, 5t for z, and 2 plus t for x. So we get this right here. And of course, our bounds go from 0 to 1 on t. So what have we done? Well, we've had an integral which has a bunch of different variables, and all the variables have now been made into t, which means if we rearrange, that we get a polynomial in t, dt, which is very easy to integrate and take the top minus bottom here, right? So we'd get 10t plus 29 half t squared. Top minus bottom is what? 10 plus 29 halves, which is 20 over 2 plus 29 over 2, which is 49 over 2. Right? But again, getting to here is probably going to be most of the marks. The second parameterization for the second line segment from 345 to 340 is done the same way. Again, take the first point, multiply by 1 minus t, take this and add the second point times t, right? And that will give you your parameterization. So x is 4, y is 4, z is 5 minus 5t. And so we get kind of lucky here, right? Because the derivative of x with respect to t is 0, the derivative of y with respect to t is 0, and the derivative of z with respect to t is minus 5. So this integral right here simplifies quite a bit, right? Because this disappears. Our x gets 3, and our dz gets minus 5. Oh, dt. So all we have to do is integrate minus 15 dt. No, I didn't. There should be a 0 to 1 here. Right? Minus 15 dt just is minus 15. I just forgot to put the 0 on the 1. Okay, so if we add the two previous values, we just get that the line integral over this surface is 19 halves. But again, there's only really two things that can happen here. Right? You want to do the line integral by changing everything to a t, or you do a line integral by moving through this x, y, z parameterization by doing by isolating for the dx and dt's and doing that swap. Okay, this is the last of it for today. We're going to do line integrals over vector fields. I'm going to let you out a little bit early. I doubt most of you will complain. But this is very interesting for physicists or generally. So who can tell me what work is? Yeah, it doesn't surprise me that none of you know the definition of work. Force times displacement, right? If I'm a force and I'm pushing a box from A to B, the work that I have done as that force is the constant force times that displacement. So if this vector field or force field represented water flow, for example, and I wanted to move a rubber duck along this magenta or this pink line, I can ask, what is the work required of this vector field to move this rubber duck along this path? And this is going to end up being a line integral. Right, so instead of having an F, which is a surface, we're now going to have an F, which is a vector field. So recall that the work done by a force F to displace, right, that is to move in a straight line, a particle from P to Q, is force times displacement, right, where this displacement vector is the difference of the vectors. This means the work done by F, right, the force field, to move a particle from some position on a curve to another position on a curve, right, if we just take our time and we chop it up into a bit, is approximately this quantity here. Now, this sort of energizes me when I was an undergrad. I love seeing complicated equations like this. But if we work through this, you'll see that it's not actually expressing anything crazily complicated. Right? This means, well, you have a curve in space, right? And you have some sort of sample time ti asterisk. So let me just call that t. So this says, this r ti says to go to some point in space, designated by some curve that you've given me. Then ask for what vector comes out of the vector field at this point, right? That's what this quantity is going to be, right? The force at some point in space. Then delta SI is the space, right? If you had a curve R, remember delta SI is the length from one sample to the next sample along R, right? So it could be curved. But what is this? What does it mean when you put a hat over a vector? Unit vector, right? So I'm saying this is the unit. I want to move delta S units in the direction of the tangent vector of R. Why? Okay, so who remembers what a linear approximation is? Slightly? Okay. We talked a little bit about this when I was farting around at the beginning of the year. Okay, so remember last year you were studying curves like this, right? And you found this line, namely the tangent line, and we said that this line is a good approximation. So this line F is a good approximation for G. Where? Well, if you're very close to this point here, right? You're getting worse and worse approximations as you move away, right? But if I were to take this and magnify it, right? The linear approximation is that line near that point. Right? But if we had instead vectors, right? If this was a curve given by RT, if I went to here, for example, T asterisk I, if I wanted to know what this is, RTI plus 1, I can instead use the linear approximation, right? I can say, well, don't actually don't actually move to there. I know that this distance is delta SI along here. So instead of actually moving along the curve, I'm going to say, well, look at the tangent direction and just move that distance along the tangent direction, and that's good enough. Right? So that's why I'm saying here. I'm saying, well, if you move delta SI in the direction of the unit tangent at that point, that's going to be a good enough approximation of the next sample. All right, so that means that the total work to move the particle from RA to RB, right, so that we have to walk along our curve and count the individual contributions of work at each position, right? We're going to get resistance from the force field no matter where we move, right? So this is why an integral is needed, because we need to count the contribution of work at all time, right? And time is a continuous spectrum. So the total work to move the particle from RA to RB along RT is approximately the sum from I equals 1 to n of the vector that is given by the force field at the point ti asterisk on our curve, dot product now, right, because these are two vectors, the next position, right, the linear approximation of the next point. And if we say that all of these distances along the curve are equal, right, because currently they're SI, so remember, we're the ones choosing the samples. So I could insist from the get-go that, well, your delta SI, the gaps on our RT have to be equally spaced. That would actually be difficult to set up practically, right? Because you'd have to do a bunch of line integrals at each point. But theoretically, it doesn't matter because these intervals are becoming infinitely small anyways. Then we can further simplify this expression by removing this delta SI and just multiplying everything by it. So what does this look like? Very close to. So this is, we've been doing the same thing all year. I've been setting up sums, and then I've been taking those sums to a limit and equating them to an integral. So if I want to take this delta S to 0, which means dividing my curve RT into an infinite amount of pieces, then we actually have this integral. Okay? By definition. Okay, but from an earlier proposition before, in this lecture, I wrote this, right, that the integral over C of some surface ds is equal to the integral from A to B of f evaluated at RT times the length of this tangent vector, right, provided that RT was the thing that was parameterizing C. Okay, so this means, so notice that this integral has the form of this integral, right? Is the integral over C of something ds. So this is the integral over C of something ds, right? So I'm just going to let the integrand here be the something of this, right? So I'm going to set f x y z to equal that expression, right? So I put that expression into here, and what do I find? Well, that this is equal to, using this proposition, the function f times the, oh, there should be two lines on this one, I reckoned. Right, so the function f times the length of the tangent vector here. So how can I simplify this now? What's another way of writing the unit tangent direction here? What is this defined as, basically? Yeah, the tangent direction divided by the length of the tangent direction. This. So what happens now? Well, I can cancel out these two guys. And I'm left with this. Right? And this is something that we can integrate. Everything would be changed to an equation in T. Then I can integrate over that equation in T. Right, so here's a real, well, here's the definition. So if you want to take a line integral over a vector field, right, so this was developed from the guise of us requiring to calculate work in a vector field. But this shows up so frequently that we just give it its own sort of name. Right? So work is a work comes out of this. Right? This is more general than the notion of work in a vector field. So let f be a vector field, and let C define a smooth curve given by RT. Then the line integral of f along C is given by this expression here, where this is a dot product. We remember what the dot product is, yeah? Scalar product. Yeah, you just take two vectors and you take their dot product and it gives you a scalar. Do you remember what geometrically this was measuring? Well, if the dot product of two vectors gives you 0, what can you intuit from that? Yes, orthogonal. Perfect. The dot product of u and v is the length of u, length of v cos theta. So if that's 0, then the theta had to be 90. So generally, the dot product is telling you how acute or oblique the angle between two vectors are. Right? When this is 0, and I think this increases your dot product and this decreases it. But it is a measure, right, of the angle that is represented between two vectors. Right? And you know that you sort of have to use your intuition, right? That this is a vector and that this is a vector, so that this dot must be the dot product. Right? There's no ambiguity here. Right? So again, really all we care about is how to accomplish these questions. Okay, so let's pass this exam with flying colors. So if you're asked something like find the work done by this force field and moving a particle along this curve, then we just have to follow the prescription that we just laid out. Right, so first we need to take our force field and evaluate it at our curve. Right, so x gets cos t, so this means that this becomes cos squared t, and y gets sine t, so minus xy becomes minus cos t sine t. The derivative of r prime t then is what? Minus sine t cos t, and therefore the work done is given by the integral from 0 to pi half of f, the field evaluated at RT, dot product r prime t dt, which is equal to 0 to pi half. How did I get? Oh, the dot product of these two things, which is minus sine t cos squared t plus minus cos squared t sine t. So we get minus 2 cos squared t sine t dt. That integrates to cos cubed t over 3 from 0 to pi half, gives us minus 2/3. Okay, and this is the last one for tonight. If I said find the integral, the line integral over this curve C, over this force field, when C is the curve, this is actually called the twisted cubic, t squared t cubed. We have RT is t squared t cubed, which means the derivative of r is 1, 2, t, 3t squared. If we evaluate f at RT, what are we going to get? Well, RF, what's RF? Oh, here's our, okay, I don't know, I didn't actually say what the force field was, but maybe we can work it out. If f at RT was t cubed, t fifth, t4, so it should be x cubed it's in the book. I have to use the teacher's solution manual. No, it could be so many different things. Yeah, x, y, y, z, z, x. Maybe I should write that down. Yeah, so our f here. F is this. I should stop doing heroin while I write these notes. No, heroin's too awesome. Y, Z. Although ice is the judge of choice here in Oz, it seems. All right, so this is that's the curve. So now everything makes sense. And so you just have to work out this fairly simple integral down here. Just by taking the dot product of this vector with this vector. So you're going to get t cubed plus 2t5 plus 3t6. You add those all up, and you take the integral, and you're left with this, and you're left with 27 over 28. Right? So again, I go through the actual integration very quickly because at this point it should be very routine. The most difficult part of these questions, again, will be the setup. Right? But I've given you 3 equations today. This one's quite important. Maybe this will be faster. That's the one you need. The other one you need is this. And actually, you only need the 2 because the 2-dimensional version of this is exactly the same. All right, so if you can remember this equation and you can remember this equation, you're fine. And they're both based, it's exactly the same thing, except you change this f from a vector to a scalar function, and this becomes the scalar product. Right? So really, if you can remember this, easy peasy. Just got to practice a bit. Okay, so have a nice break. See you in 2 weeks. I'll be on campus if you guys need help. I suggest that you do actually try to get some work done over this break. Or else. I'll see you in a couple weeks.